Hi everybody. In this video, I'm going to talk about some useful limits which you can use in calculation. Also, it's important to know them because of the exam. So first, I would like to count two important limits which uh, we have to know. The first of it is you can know is we call them wonderful limits. The first wonderful limit is limit x tends to 0, sine x equals to sine x divided by x equals to 1. And the second limit is limit x tends to infinity, so 1 plus 1 out of x to power x equals to number e. So both of these limits are useful. They are called wonderful limits. So most of limits come to the use of this two formula. So the first one you can see is the limit in case of sine x divided by x. So when x tends to 0, we get 0 divided by 0. It's an undetermined form like 0 divided by 0. But you can see in our case, it's proof that it is number 1. And the second one, again, when you put instead of x plus infinity, you're going to get here 0. This becomes 0. So we get something like 1 power infinity. But in any case, it's also undetermined case. And this also comes to number e. So I'm going to start with the easy case of limits. So this example is not an example when we do the canceling, of course. But with this example, we are going to also know that what does limit serve for? The main idea, the principal idea of the limit. So you can see, of course, if you place here 4, you're going to get 0 divided by 0. This is undetermined form, but in any way, we can eliminate this remove this undetermination by factorizing the numerator and denominator. So if you factorize numerator, you're going to get x minus 4 times x minus 2. And for factorization of the denominator will give us x minus 4 times x minus 1. When you do the canceling here, you're going to get obviously limit x tends to 4, x minus 2 divided by x minus 1. And if you place instead of x, you place 4, you're going to get 4 minus 2 divided by 4 minus 1. It is 2 divided by 3. So in this exercise, we can see that the limit serves for elimination of undetermined form. So if we have the undetermined form, we eliminate it by factorization, and usually we cannot do it with the function. So if we have the function, we cannot do it. But we can do with limits. This word limit here stands for the right. It grants the right to do this elimination here. So the second example is a little bit harder than the first one. You can see if you put instead of x, you put 0, you're going to get under root 1 plus x. 1 plus 0 is 1 minus 1 divided by. So it's undetermination of the form 0 divided by 0. However, we are going to eliminate this undetermination. Let's see how. So for some limits, we use different methods for calculation. Here we are going to apply a method which is called substitution. So we are going to substitute the x here with another one. But let's do what we can do, which substitution works here. So what if we substitute the numerator with a certain number, with a certain variable t. So for example, let's substitute numerator 1 plus x minus 1 with one variable t. Then what we get here, under root 1 plus x equals to t plus 1. So we get here under root, so if you square it, 1 plus x squared equals to t plus 1 square. So from here, 1 plus x equals to t plus 1 square. And x equals to t plus 1 square minus 1. So we have x in the denominator. So instead of x, we can put here this number. So in this method, if you can see x tends to 0, then x tends to 0, let's write x tends to 0. Then from this substitution, we are going to get t equals to 0 too. So you can see when x tends to 0, then we have t equals to 0. So in this case, let's see our limit becomes, it's equal. I'm going to write here. So limit t tends to 0 again, because x tends to 0 reveals t tends to 0 also. So what we have after our substitution, in the denominator, we have t plus 1 square minus 1. And in the numerator, we have t. So we substitute the whole numerator by t. Then what happens? Let's see. Limit t tends to 0. Let's expand the bracket in the denominator, t squared plus 2t plus 1 minus 1. We get t here. So 1 and minus 1, they cancel. What we have finally, limit t tends to 0, t divided by t squared plus 2t. You can see that you can factor out t, and after you factor out t, you're going to get something like this. Limit t tends to 0, 1 out of t plus 2. So obviously, instead of t, you can substitute 0 here. There is no undetermination here. So 1 out of 0 plus 2. So the answer is 1 out of 2. So this limit is going to be 1 out of 2. So what we used here, we used a method. Probably you don't know this. We use this method of substitution for calculation of these limits. Do not forget, we are going to use this method for not only limits, but also with calculations of different types of problems related with integrals also. Now let's see something again different. So limit x tends to 0, 1 minus cosine x divided by x squared. So again, I would like to remind you the first wonderful limit that we use here. So obviously, if trigonometry is involved, then it's natural to think that 1 is equal to 1. So if trigonometry is used, it's natural to think that we have here this wonderful limit. So let's try to use it. But this form is not relevant, is not seen like this. So we can bring it by some trigonometric change, simplifications to this form. Let's do how. We know that we well know that cosine x is equal cosine squared x divided by 2 minus sine squared x divided by 2. So we know it from our actually from our school years and from our exams and so on. So instead of you can know that instead of cosine square x divided by 2, we can substitute 1 minus sine square x divided by 2 minus sine square x divided by 2. So obviously we get 1 minus 2 sine square x divided by 2. So if we place it here in the numerator, let's see what happens. We are going to get limit again, x tends to 0. When we place it here, we are going to get 2 sine squared x divided by 2 divided by x squared. Now we can see that it is in a relevant form, so we can use this limit. So it's going to be something like sine square x divided by 2. We have sine squared here, so obviously x squared will also participate, but we have x divided by 2. So here you see x and x, they are equal, yeah? In order to get 1 here, we have to equalize them. So x divided by 2. So it's obvious to think that we can get here x divided by 2 squared. But however, you cannot get it right here if you don't multiply by 4. So if you multiply by 4, it's okay. Do not forget to put number 2 in front here. So x divided by 2 squared times 4. Because x squared divided by 4, 4s are cancelled, we get the same thing. So everything is okay here. So these 2 and 4 you can cancel here. You're going to get here 1 out of 2 times. We can factor out from limit. We know this property. X tends to 0. So obviously, I'm going to write it like this. Sine x divided by 2 divided by x divided by 2 squared. So this is 1. So instead of this expression, I can write 1. I know this. So it is 1 out of 2 times 1. So obviously, I got here 1 out of 2 answer. So let's do number 4. Number 4 is another of the type of limits that sometimes come across here. This is used especially in derivatives when we prove the derivative of logarithm function and so on. So it's useful to know such a limit. How we can do this? Again, I'm going to use here the substitution method. So let's try to do substitution. Before we use the substitution method, I'm going to also remind you second wonderful limit. So the second wonderful limit, if you remember, it's x tends to infinity or 0. You can write this 0 case 1 plus x to power 1 out of x. So if you remember in the first slide, when we talked about the limits, I mentioned this with infinity. So infinity, you can do it 0 by x tends to, when x tends to infinity, you can get here 0. So it means that you can write it limit x tends to 0, 1 plus x. And this x you can change to 1 out of x. So it is possible here. So this limit equals to e. We are going to use it. So let's do substitution. Again, for this purpose we are going to use substitution. 2 to power x minus 1 divided by x. So this is going to be, if we multiply, if we do here the substitution, the situation, let's see how it's changed for our favor. So 2 to power x minus 1. We denote by t. Let's denote it as t, new value t. So from here, 2 to power x equals to t plus 1. And x equals to logarithm base 2 t plus 1. So again, if x tends to 0, then obviously when x tends to 0 here, if we place here 0, we are going to get 2 to power 0 minus 1 equals to 2, which makes again 0. So t also tends to 0. This is something that we should keep in mind. So it's equal. We write our new limit after substitution. Limit t tends to 0. 2 to power x minus 1 is actually t divided from our substitution. Here you see it is t divided by x. So x is, we substituted it logarithm 2 base 2 t plus 1. So it's going to be, again, limit t tends to 0. We can write it as like this, 1 out of 1 t. So we do some basic algebra here, t plus 1. It's equal, limit t tends to 0. T tends to 0. So we can write it like this, 1 out of logarithm 2 base 1 plus t to power 1 out of t. So you see, we came up to this, our limit looks like this. You see 1 plus t times 1 out of t. So if we can place this limit inside here, then we are going to get what? 1 out of logarithm 2. So instead of this part, you can see when t tends to 0, we can get e. So e, but doing some simplification, we can write it as ln natural logarithm 2. So 1 out of logarithm base 2e is natural logarithm 2. So we can well write it. So the answer here is natural logarithm 2. Logarithm 2. Okay. So again, it might be difficult from the first start to do this, to understand this, but I would advise you that you should go through it by yourself. So change 2 by 3 and do it by yourself. Obviously, you are going to get something new there. And we have some more limits. The limit x tends to 0, 2 arc sine x divided by 3x. So we know that limit x tends to 0, sine x divided by x is also 1. But if we do such a substitution here, for example, sine x equals to t, so it's going to give us x equals to arc sine t. So obviously we can do it with some conditions, of course, with where the arcsine function is defined. So if we are talking about the closer interval of 0, open interval of 0, so it's possible. It's possible for arcsine function. So if x tends to 0, we can see here if x tends to 0, sine 0 is also t. So then t also tends to 0. So in this case, our function, our limit becomes limit t tends to 0. It's going to be 2 times, arc sine, let's write this one first to keep it clear. So x is arc sine t, so it's going to be arc sine t here. So we are still doing this one, arc sine t, and sine x is t. So obviously you can rewrite it like this, limit t tends to 0. We can write it like this, 1 out of arc sine t divided by t. So it's 1. We know it from here, it's 1. So it's equal to 1. So we proved that actually we can write that limit t tends to 0, arc sine t divided by t also gives us 1. So if we apply this to our given function, then it's going to be limit, again, x tends to 0, 2 out of 3 arc sine x divided by x. This limit gives us, it tends to 1. We know we have already proved it. So it's going to be 2 out of 3. We can use the same thing with tangent function. So limit, let's try to find this limit x tends to 0, tangents x divided by x. So it's going to be, we know that it is limit x tends to 0. Tangent we can write as sine x divided by cosine x times x equals to, so we can write it as limit x tends to 0, 1 out of cosine x times sine x divided by x. So this limit is 1, we know it, it's the first wonderful limit. So when you place, so we get in the end limit x tends to 0, 1 out of cosine x times 1. So cosine x, we know that it's instead of x, you can write 0. You're going to get 1 out of 1. So the answer is going to be 1. So obviously, if limit, we know that limit, this, the true fact that this limit exists also gives us the possibility that the limits also exist. It's 1, and also divided by x equals to 1 also. So well, that's all for now. I hope you enjoyed these limits. They are important limits that you should know. If you are doing the limits, you have to know them. So I hope they were useful. So hope to meet you in our next videos. Take care. See you. Bye.